Hello pre-calculus students, and welcome to our continuing lesson on rational functions. And in this video here, we're going to take a look at a more complicated example. In the previous video, we talked a lot about functions that only have x in them. Now we're going to deal with something that has x squared in them. So, and if you recall from the previous video, one of the things that we care about here when we talk about end behavior is the growth of the function. So let's say as x gets large, the numerator here is just going to be dominated by the highest power, and the denominator will also be dominated by the highest power. So as x gets large, the leading term becomes the end behavior. And I should say leading terms, plural. Okay. So if we want to find out the end behavior of the function g of x here, well, we can just look at the leading terms on the top, which is 2x squared over x squared. Now, this is not saying that these two functions are the same thing. It's just really saying that they behave the same way as x gets large. Okay? And this is going to come out to 2. So as x gets large, g of x is going to approach 2. So we can say that the limit of g of x as x approaches infinity is going to be equal to 2. And the limit of g of x as x approaches negative infinity is also going to be equal to 2. Okay, so this captures the end behavior, and it also tells us the horizontal asymptote. For rational functions, those two are the same thing. Now let's take care of some other stuff here. So we're asked to find, let's see, the intercept. So let's start with the y-intercept. And that's simple enough. We'll just do g of 0. And again, for rational functions, because both the top and the bottom are polynomials, when you substitute 0 in here, anything that has x in it is just going to be 0. So you're going to have 0 plus 0 minus 2. On the bottom, you're going to have 0 minus 1. So this is just going to be equal to 2. Okay. Now the x-intercepts, well, by definition, the x-intercepts occur when y equals 0. So we set g of x equal to 0 and solve for x. But the nice thing about this is because whenever the numerator is 0, the entire fraction is going to be 0. The fraction equals 0. So we really just have to worry about the numerator. So I'm going to do the note here on the side. So if you were to solve this, what you're going to do next is you're going to multiply both sides. You're going to say 0 times x squared minus 1 equals 2x squared plus x minus 2. So you're taking this denominator, multiplying by both sides, and you're going to end up with 0. Okay. So what it's really saying is just you don't have to really worry too much about the denominator when you're talking about x-intercepts. Just set the numerator equal to 0. Okay. All right, so now that we have that set up here, we can just solve this using your favorite method. And I'm going to use the quadratic formula here, which it's not really my favorite method, but it'll do the job. Opposite of b plus or minus square root b squared here is 1 minus 4 times a times c, all of it over 2a, which gives me negative 1 plus or minus the square root of 17 over 2. So these are my zeros. This is the y-intercept, and this is these two numbers here are the x-intercept. So x-intercepts, asymptotes, sort of. The domain and range, we'll worry about that in a minute. End behavior, we just took care of that. Okay, so remember that the end behavior is the same thing as the horizontal asymptote. Now let's worry about the vertical asymptotes. So for vertical asymptotes, we set the denominator equal to 0. Because vertical asymptotes are points that are undefined on the graph, okay, so we want to set the denominator equal to 0. And then solve for x. X squared equals 1, x equals the square, plus or minus the square root of 1, which is plus or minus 1. So these are the two vertical asymptotes. Now what I want to do here is to write the vertical asymptotes using limit notation. So let's get to that. And it is possible to sort of figure it out, but it is very difficult at this point. So we're going to use our graphing calculator here just to help us do this a little bit quicker. You type in the function here. 2x squared plus x minus 2 divided by x squared minus 1. Okay. Let's start out with the standard window. And that looks a little bit weird, so I'm going to sketch it out here so that we can see it a little bit better. Okay. And again, this is kind of why we have to try and do things algebraically so that we can make sense of the graph, because if you rely on the graph too much, it can trip you up sometimes. So we know these are the vertical asymptotes. We know that there is a horizontal asymptote at 2. And the graph, from what I see, looks like this. It goes this way. It goes down this way. Okay. And in fact, it has another piece right here that goes down. It's going to touch at 2 exactly, and goes down here. Okay. I know this touches at 2 because that's the y-intercept. Okay. So now we can write the vertical asymptotes, and since there are 2 of them, we have to write 4 different limits, and it's a little bit annoying, but it helps describe the entire graph in full. So first is the limit of f of x as x approaches 1 from the right. Okay, so going left, this is what people get confused about. From the right means going left. So you start out from on the far right and you go towards the left. From the right is what the plus sign means. And as you can see here, as you get closer and closer to 1, the graph spikes up to positive infinity.
Good morning, staff students. One quick announcement.
And then the limit of f of x as x approaches 1 from the left, meaning what happens when we stand on any part of the graph and we go closer and closer towards 1? Well, f of x gets closer and closer to negative infinity. And then that only takes care of the positive 1. Now let's deal with negative 1. So what happens as what is the limit of f of x as x approaches negative 1 from the right? So as we go closer and closer to negative 1 from the right, you see that it also spikes up to infinity. And then the limit of f of x as x approaches negative 1 from the left with this minus sign. So from the left, getting closer and closer to negative 1, it actually shoots down to negative infinity. Okay. And so the vertical asymptotes, we can do this to figure it out, but if you really want to describe the behavior in full, you have to use limit notation. Okay. And then one final thing we got to do here is answer the question about range and domain. Well, you can see the graph certainly helps a lot. The domain is everything except negative 1 and positive 1. So the domain here is everything from negative infinity to negative 1. Then anything between negative 1 and positive 1. and then anything from positive 1 to positive infinity. Whoops, I should show you that. Okay. And then the range, now the range can sometimes be deceptive, which is why we need to write this in limit notation, because if you have this limit here, you should be able to reconstruct the graph. And in this case, we can see that because of this middle piece here, it's going to cover everything. So the range here is just negative infinity to positive infinity. Okay, students, well, thank you for watching. We'll explore these concepts a little bit further in the next video. Again, this material, there's a good intuition for all of this, but to really be good at it, you have to use precise language, you have to use precise definitions, including some of the mathematical definitions, which may not look pretty, but they give us the full and complete picture of what these functions do, so that if we need to use them for practical problem solving, we will be able to do so. So thanks for watching again. Have a wonderful day.